Hi everyone, welcome to week 13. Last week we concluded our study of series and sequences. The last thing we did was a bunch of tests for checking whether things, when infinitely many things are added, if they converge or not. Today's topic is power series, so we're going to build up on our knowledge of a series and define a specific series, which is of the form summation Cn x to the n or C0 plus C1, x plus C2, C3, etc., where x is the variable and Cn's are constants, which are called the coefficients of the series. So just as with any other infinite series, they can be tested for convergence or divergence. Some power series may converge for certain values of x and may diverge for other values of x. So our goal is to understand these kind of series, understand what happens when we change these coefficients and have them to be a certain value. Um, how does that affect the convergence of the series? If we let all the values of x for which the power series converges to be the domain of the function, then that function can be represented as the function can be represented as a power series, which is very helpful because it means that um, I have a very simple expression for any kind of function. Now let's look at an example. Let's say I let all the coefficients be 1. What do I get? I get 1 plus x squared plus x cubed plus x to the 4, so on. But this is familiar because this is a geometric series with a1 and rx, meaning this actually sums to 1 over 1 minus x. And this is only if the value of x is less than 1, right? So it converges if the absolute value of x is less than 1, and in that case the function 1 over 1 minus x can actually be written as this very nice power series. And so you can think of it as an approximation. Okay, for what values of x is this particular series convergent? So we're going to have to resort to some of the tests we have seen before. The presence of this factorial sort of implies that maybe I should consider ratio test. So ratio test says take the limit of the n plus 1th term over the nth term. That's going to be n plus 1 factorial x to the n plus 1 n factorial x to the n. This cancels out, this comes out to x, this cancels out, and you get n plus 1. So this is limit n goes to infinity n plus 1 times x. This is going to go to infinity regardless of x, right? And what does the limit test say about when the ratio is more than 1? It is divergent, which means that for no values. Okay, so this is never going to be convergent. Let's look at another example. For what value of x does this series converge? Again, let's use ratio test one more time. Ratio test says that the ratio is going to be limit of x minus 3 to the n plus 1 over n plus 1 divided by this limit. Now this cancels out, and I'm left with limit n goes to infinity n over n plus 1 times x minus 3. This we know is 1. So this ratio is x minus 3, and we know by the ratio test this converges if the ratio is less than 1, or x minus 3 is less than 1, greater than negative 1, or x is less than 4 and greater than 2. Okay, so for these values converges. For other values of x, it diverges. So our knowledge of series can be used for finding when certain power series converge and when it does not. This leads us to a definition for domain of convergence. That's basically all the values of x for which it converges. Bessel functions are important. They arise in many physical phenomena like solving Kepler's equation for planetary motion. And we'll do an example where we find the domain of the Bessel function of order 0, which is defined by this particular formula. So finding the domain of this function means finding the values of x for which it converges. And again, I'm going to resort to ratio test. If I resort to ratio test, this is going to be n goes to infinity, x to the 2n plus 2, 2 to the 2n plus 2, n plus 1 factorial squared, which I can rewrite as n plus 1 factorial times n plus 1 factorial. And it's a division, so I flip the second fraction, which is 2 to the a, which is basically an. And first thing I notice, this cancels out, leaving me with an x squared. This cancels out, leaving me with a 2 squared. And these cancel these out as n plus 1, n plus 1. This comes out to limit n goes to infinity of x squared over 4n plus 1 squared, which is 0 for all values of x. This means that the domain is everything. Because this is always less than 1, which by ratio test means that it converges for all values. So it's pretty neat that we get that the domain of convergence for the Bessel function is everything. We're going to look at some theorems and definitions in the next video.